Hello students, welcome to Shankar's Physics Tutorials. Today we are going to see about 12th physics in ray optics. We are going to see about focal length of spherical mirrors. So I'll write it here. So we are going to learn about focal length of spherical mirrors. Okay, so let me draw a concave mirror and the center is going to be the pole, and I'm going to draw a principal axis. So principal axis is a line that passes through center of curvature and principal focus. So C is the center of curvature, F is the principal focus, and P is the pole of the mirror. So let us assume paraxial rays fall on the mirror. So what is the meaning of paraxial rays? Nothing but these are the rays that are incident close to the pole of the mirror, close to pole of the mirror, that makes small angle, that makes small angle with the principal axis, with the principal axis. So this is nothing but a definition given to paraxial rays. So let me draw some parallel rays like this, and these rays are going to incident onto the mirror at some points. Let me name the point as capital N and capital M and capital A. Okay. So after being reflected, it has to converge at a point. Okay. That point is nothing but called as the principal focus of the concave mirror. So let me draw a normal. Usually a normal is nothing but a perpendicular drawn to the point of incidence, and usually for a spherical mirror the normal is drawn through the radius of the spherical mirror. That is nothing but it has to pass through the center of curvature and it should meet the point of incidence. Okay, so whenever you want to draw a normal to a spherical surface, always draw a line that passes through the normal that is going to incident onto the spherical surface. So this makes some angle I. Let me write it as I. And after reflection, the ray passes through a point on the principal axis that is nothing but principal focus. So this is taken as the incident ray and this would be the reflected ray. So this is in the case of a concave mirror. What happens in the case of a convex mirror? So let me consider again all these terminologies: pole and principal axis. This is principal focus and center of curvature. Again, whenever a parallel ray is going to strike onto the surface for this convex surface, what happened? Again, the light rays are going to get reflected. So let me draw a normal. So always a normal is drawn through the center of curvature. So what happens is the light is going to get reflected. But how does it is going to go? So I'm going to draw it in such a way that the light rays are reflected that appears to emerge from the principal focus. So it is going to be going like this. So it is making some angle of incidence I and angle of incidence R. So here I have not drawn to the scale, but you please note that angle of incidence should be equal to angle of reflection. Okay, so the light ray, so let me redraw that. So for a convex mirror, when paraxial rays fall onto the mirror at the point of incidence, after reflection, it appears to diverge from the principal focus. This point we should learn. Okay. So this distance from the pole to the principal focus is nothing but the focal length of the mirror. So whatever mirror it can be, this focal length, the symbol used for it is equal to F. So we know that F is equal to R by 2. So we are going to learn how to derive this from the geometry. Okay, so before that we should learn what happens when parallel paraxial rays fall onto the mirror. So that is what we are going to see now. So when parallel paraxial rays fall onto the mirror, fall onto the mirror, what happens? Okay, that is what we are going to see. So for that, let me take again a concave mirror. So we should learn to draw all these things. Okay, it passes through the pole, and this is the principal focus, and this is the center of curvature. So how to draw a parallel paraxial ray? Again the same thing. I'm going to take two rays. One ray is going to incident at any point on the mirror like this. Another ray, it is going to strike the pole of the mirror. Okay, so how it is going to behave? This ray is going to make small angle. This particular ray, no, that is going to incident at the pole, it makes small angle I with the principal axis, and after obeying the laws of reflection, it is going to get reflected back in this way. Okay, that is going to make the same angle, which is angle of reflection. What happens to this point? This ray, no, that is going to incident, let me name the point of incidence to be M. This ray, again after reflection, it, instead of passing through a point on the principal axis, let me draw some other different structure. I'm going to introduce a term called as the focal plane here. So what is nothing but a plane? It is nothing but a two-dimensional structure like this. Okay, so instead of passing through the principal focus, this ray after getting reflected, it is going to meet this second reflected ray at a point. Okay, at a point like this. This is the point. So this point is not actually passing through the principal focus, but when I consider a plane like this plane is nothing but a plane passing through the principal focus, which is perpendicular to the principal axis. So this is the principal axis. Perpendicular to it, I'm going to consider a plane, that is two-dimensional plane. That plane should pass through principal focus. So when these two reflected rays are going to get converged at a point on the plane, this plane is called as the focal plane of the converging mirror. Okay, basically concave mirror is a converging mirror. So in generalized, we can say this is the focal plane. The same is applied for the convex mirrors as well. Okay, this is for concave. The same is applied for convex mirror as well. Now what we are going to learn is, let us learn how we are going to derive f is equal to r by 2. For that, we are going to use some basic geometry that we have studied in our earlier grades. So first we should learn the diagram for it. Let me draw the diagram. So let us learn the geometry of reflection of the spherical mirror. So this is the mirror I have. Let me consider a ray parallel to the principal axis that strikes the mirror at the point M. Okay, and let us draw a perpendicular through the center of curvature to the point M. This is going to make an angle of incidence. Let me write as I. Okay, so we have learnt in our earlier grades, when two lines are parallel to each other, and this line is the transversal that is going to cut the two parallel lines, I can write, if this angle of incidence is I, this angle is also going to be same. This is theta, this is also going to be theta, because they are the alternate interior angles. So if this is I, this angle is also going to be I. Okay, so this ray is going to touch the principal axis. It should go like that. Okay, this is the normal to the point of incidence. Okay, what happens after reflection? It is passing through the principal focus. So let me take a different color to draw that. So this is the reflected ray, and it makes the same angle of incidence. That is, angle of incidence is equal to angle of reflection. Now, what we are going to consider is, what is this angle? I want to find what is this angle. Again, I'm going to draw. So let me take this as one parallel, this as another parallel. So I'm going to draw two parallel lines. And now the transversal is going to be this reflected ray, right? This is the transversal. What is this angle? Okay, this line is going to make an angle of what with the parallel ray? This is R, this is I. Both angles are equal. So I plus I can take it as 2I. So this reflected ray is going to make some angle of 2I with this parallel ray. So I can draw this, write this as 2I. So what is this angle? This is alternate interior angle. So this angle is also equal to 2I. So I have this 2I. Okay, now what I'm going to do is, I'm going to draw up a perpendicular from M to the principal axis, and I'm going to name this point on the principal axis as D. So here what we are going to consider is this MD is perpendicular to the principal axis and D is so much closer to P. Okay, and please have that in mind. We are going to make some approximation later. So now I have how many triangles? First one, I have this triangle. So let me trace this triangle. First triangle is I have this one, M, C, right? This triangle. M, C, D. I have this one triangle. And next, what is the triangle? I have M, F, D. That is going to be the next triangle. Okay. So I have now two triangles. What are the two triangles? Triangle MCD and I have triangle MFD. Okay, I have basically two triangles. So now what I'm going to do is, since this angle is I, this is also R, this is also equal to I, this angle is I and this is 2I. This is what we have taken. In your book, NCRT book, they have taken this angle to be theta. So no confusion. So we will also take theta to avoid confusion. So this is theta, this is theta, this is theta, and this would be 2 theta. Okay. So what is tan theta? Tan theta is opposite side by adjacent side. So opposite side for this triangle is MD divided by adjacent side is CD. Likewise, what is tan 2 theta? Tan 2 theta is equal to, again, the opposite side, which is MD divided by the adjacent side is FD. Okay. Now, what we have said is, usually these rays are paraxial rays which are closer to the pole of the mirror. So that means it is going to make small angles, and we have learnt and we should be aware that for small angles, what should be the angle? This angle can be lesser than some about 10 degree. If the angle made by the ray with the principal axis is going to be roughly less than 10 degree, I can consider this angle as small angle. For small angles, I can approximate. Tan theta is approximated to theta. Likewise, tan 2 theta is approximated to the same angle 2 theta. Okay. So I can, for small angle approximation, I can take theta is equal to MD divided by CD. And what is tan 2 theta? So 2 theta is approximated to MD divided by FD. So what I'm going to do is, I'm going to substitute this theta value here. So what I will get? I will get 2 times MD by CD is equal to MD divided by FD. So MD is common. I can cancel this out. So I'm getting 2 by CD is equal to 1 by FD. So I want to know what is CD and what is FD. Let me again go to the diagram. So what is FD? Since D is closer to P, I can consider FD is nothing but equal to focal length of the spherical mirror. Since D is very much closer to the pole of the mirror. Likewise, what is CD? CD is nothing but this distance. Similar to PC, no? It is nothing but the radius of curvature. So I am going to substitute FD as small f, CD as R. Okay. So CD as R, I am going to substitute here. So 2 by R is equal to 1 by F. So what is F? I am going to take the reciprocal. F is equal to R by 2. So this is what the approximation. Since D is closer to P, what I am going to take? CD can be taken as R, FD should be taken as smaller. So from this geometry, we have derived the focal length of the spherical mirror is equal to half of the radius of curvature of that spherical mirror. Hope this video helps you. If you like this video, please like, share and subscribe my channel and spread the word to your friends. Thank you.